Okay, welcome everybody.
Thank you.
Thanks for coming here. And I'll present mostly about what I've done so far in my PhD, but I wanted to make it valuable for you and hope that every one of you can take something out of this. And so I'll talk mostly about the brick imaging, but I will also try to feed in some interesting things which are relevant for other PL measurements. I want to start by showing comparison to how we image the properties of humans. And I wanted to first show you this image, and I want to ask you how you think this image is taken. Anyone a guess?
X-ray.
That's right. That's an X-ray image. This one? No, it's actually a CT image. But the MRI is very different, very similar. And this one? That's right, so it's a PET CT image. So we get the human properties inside out and can image them. How do we image properties of silicon? What is this image? That's right, so it's a TM image. We can measure the lattice structure by electron-electron interaction. If we then look into how can we image material device properties elsewhere, we sort of end up with DLIT, so that's log-in thermography or carrier density imaging. And we can also scan by using EBIC or microwave photoconductance, quasi-steady-state photoconductance, or LBIC. But the ideal technique to image electronic properties, which means minority carrier properties, is PL imaging, and we combine that. We can see that if we look at an optical image of a monolike waver, where we don't see any internal structure, and compare that with a PL image of a monolike waver. So here on the left we see just the reflection of the ambient light, basically. And here we see the laser-generated band-to-band emission. What we see is that the PL signal here is actually proportional to the minority carrier lifetime in each of the pixel, if we assume low injection. So I want to outline my talk, and I will first talk about the spectral imaging of silicon bricks. And I will show a proof of concept study, show a study about overcoming experimental limitations, and I will quantify in another study some physical limitations of the technique. And I will then go further on the inline inspection and sorting of S-cut wafers. And I will also show some examples of how we can characterize next generation cell structures while using PL. I will emphasize on the first three spots because that's what my PhD is about, but I will also discuss some of the further points. So why do we want to measure silicon bricks? If we just look at an optical image of a brick, oh, here's an ingot and then it's sliced into bricks, we can't really see any of the properties as I've shown before. So it's a big question mark what the properties will be. But the questions in solar PV are like, are the bulk lifetimes sufficient? Is the doping range right for the solar cell process? What is the dislocation density? What is the ion contamination? Where do we need to cut off? Where do we have the dead zones, if any? What are the suitable parts for high efficiency devices? And what efficiency can we expect by using a certain type of waver? And finally, what are the costs and the profits can we expect from each part of the brick? So these are quite relevant questions to be answered, and my research is trying to put more light into that and using PL imaging for that. So what are the challenges if we look at a silicon brick? Well, we can first say, oh, it's a very big sample, and we should be able to measure that easily, but actually the surface is bare, so if you want to measure a PL image, as I've shown here, this is a qualitative image, we have the trade-off that we actually measure very low signals, and especially in the red zones. They're on the top and the bottom of the brick, and we measure very low signals. I've calculated the PL signal as a function of the surface recombination velocity, and we can see that normally we have bare surfaces with surface recombination velocities of 10 to the 5 to 10 to the 6 centimeters per second. If we would passivate the surface, we would be able to have PL intensities which are more than 100 times higher. And this is a very good example of how it's actually also happening on silicon wafers, that we can have a much higher signal if we passivate surfaces. The calculation would give quite slightly different numbers. That's sort of the same ballpark. We can increase the PL intensity by about 100 times if we passivate the surface. We can increase the signal if we use a larger excitation wavelengths. So here I calculated the PL signal as a function of excitation wavelengths, and we can double the signal if we choose 900 nanometers instead of 800 nanometers. But this diagram is logarithmic, so we can't quite compensate the bare surface by just increasing the excitation wavelengths. And first of all, I want to discuss the proof of concept study, which some of you might know already. So I present the core of the technique, how we can image the bulk minority carrier lifetime and the doping of the silicon brick, and I will go along this publication. So if we want to go from qualitative to quantitative images, then we see here a qualitative image of a brick, and what we see is pretty much just the PL intensity. So it's a pure intensity image. We have to integrate over about 30 seconds, which I said before, the signal is very low, so we have to measure fairly long times. And the resolution is about a 0.15 millimeters. And we can already see on the qualitative image crystal structure, basically effective lifetime, and high impurity zones. But if we then want to go to a quantitative image, here a bulk lifetime image, we need to feed them some physical modeling in order to quantify the pure intensity images. So in order to do that, we model the spectral PL response of a brick. So we now not just look at the pure intensity, we look at the spectrum of the PL and quantify that with a physical model behind it. For the people who want to know details, like the assumptions we've put in is a simple one-dimensional model. We assume bare surfaces, obviously is infinite depth, monochromatic excitation, a thin surface layer, which is a surface damage layer, which is below 5 microns after polishing, and non-injection dependent bulk lifetimes. And we include temperature dependence of the absorption coefficient and mobility, the free carrier absorption, surface recombination velocity, excitation, filter selection. So if we start with the modeling by looking at how does the excitation profile look like, how do we excite excess carriers, and the excess carriers are the source of the PL band-to-band luminescence. So we need to know what's the profile, the depth profile of the excited carriers within the brick. We can, like in literature, we can find a solution for this problem. It's an analytic solution, and we can feed that into our model. And if we plot that, it looks like this. Depending on the bulk lifetime, we get a depth profile. And we can see here already that the depth signal increases with bulk lifetime. So whereas the peak here increases as well, but not as much as it does back here. And that's already the signal of the bulk lifetime signal. Because in this equation we have the diffusion length included, which is function of bulk lifetime. and we can then feed back to the PL being dependent, being a function of bulk lifetime by integrating over the depths and all the wavelengths. We can then feed in the luminescence emission, which we can describe, the excess carrier profile, the reabsorption term. That's like the luminescence is reabsorbed on the way out through the sample, and we measure experimental apparatus spectral dependency, and we can then integrate that analytically, which Martin Green has done and published, or we can do it numerically. That's equivalent. If we use the analytical equation to the model, we can then basically describe the PL spectrum very precisely as a function of bulk lifetime, which I've done here for 3 values. And you can see that the spectrum changes on the left side of the spectrum depending on bulk lifetime, and that's what we try to measure in our technique. So what we do then experimentally is that we measure 2 images, one with a short pass and one with a long pass filter, and we put that into a ratio. And that has several advantages. It cancels out a lot of, like the doping constant, it cancels out refraction properties, and we can then plot the transfer function of this intensity ratio as a function of bulk lifetime, which allows us then to transfer measured intensity ratios into bulk lifetimes. And some nice aspects of this is that the gradient is very steep for a very broad lifetime range, which means that we can use this technique fairly well for a wide range of bulk lifetime, which means we can measure multicrystalline samples as well as monocrystalline bricks. So the proof of concept images, here I show a bulk lifetime image of a silicon brick, multicrystalline brick. We can see central structures with high lifetime grains and lower lifetimes on the top and bottom. And I can transfer that also into a doping image by a simple equation, and it shows us the doping increasing with the height of the brick. This doping is scaled by using resistivity measurements, because the transfer into doping is just relative. I don't want to go into much detail here. I'm just showing these proof of concept results, and just want to come back and say, what have you learned so far to remind us. So we use the PL spectrum, know that it contains lifetime information. We measure 2 filtered images, model the PL intensity ratio transfer function, and can then transfer the images into lifetime and doping images. Remaining issues are blur the top and bottom region and the absolute accuracy. In order to overcome experimental limitations, we looked further into the details and published the results in this publication. So at the image before, we could see that especially the top of the bottom of the brick had unrealistically high lifetimes. And we first thought it could have been defect luminescence, but I accidentally almost found that if we cover the brick and just measure parts of, illuminate part of the brick and measure part of the brick, and then slowly uncover the brick and measure, we can see that the signal here on the sides and here, as well as under where it was covered, increases with the total amount of uncovered brick, which basically means that quite a large amount of the signal which we receive from the brick is actually scattered within the CCD. So we needed, and that would mean that signal from the center of the brick, where the high lifetime regions are, scattered to the top and the bottom of the brick and measured over there. And an inaccuracy would also result from the fact that this happens more with the long pass filtered images. You see this increases much higher for the long pass filtered images than for the short pass. this is basically because we measure silicon with silicon, and the quantum efficiency of the CCD is decreasing very, very quickly towards higher wavelengths. So we have a larger scattering effect. So we investigated that further, and I measured the light spreading of 2 localized illuminations, and with 2 filters, so the short pass filter and the long pass filter. And these were exactly the same filters as we used for the 2 images. And we can already see very clearly that the scattering is much more pronounced with the long pass image, but also existent for the short pass image. Then we tried to quantify the spreading, and we measured the point spread function. And we illuminated the CCD with different types of apertures and scaled them on the top of each other so that we got a point spread over like 6 orders of magnitude for both short pass and long pass. And you can see that the long pass image has a wider spread. And this is in sort of a methodology which wasn't published before for PL imaging, and which also affects waver images. And we then use these point spread functions in the deconvolution algorithm, which basically means we take the as measured image and we then use the point spread function to apply a reverse Fourier transformation and come up with a deconvoluted image which tried to calculate back what had been done to the image experimentally. And we can see a better, an increase in contrast and less image blur, and even more pronounced for the long pass image as expected. If we then put that into ratio, we can see that the as-measured image from the proof of concept study could be improved a lot, having much more crisp, better contrast, more details, and especially top and bottom coming out more realistically. It's very low lifetimes. So this is a bulk lifetime image again. So if we compare them directly and look at the cross section, if we average the line scan, we can see that especially on the top and bottom, the average signal decreased a lot, which is more in better agreement with QSSBC measurements. And now to refer back to waver measurements, this deconvolution and increasing the contrast, reducing the blur has quite a high impact on wafer measurements as well. And there's one study by Mitchel from Fraunhofer ISE. He tried to estimate efficiency potential of multicrystalline wafers, and he saw that he couldn't use just as measured wafer images. He needed to apply a short pass filter, which basically has a similar effect to deconvolution, which just reduces the signal strength a lot. And then he was able to quantify the intensity and to the model much better. And a colleague of mine at ANU also started looking into measuring point spread of wafer measurements, and he basically compared the point spread of an edge signal with non-filtered and different filtering and reverse and a deconvolution algorithm, and he showed that he could sort of increase the contrast and decrease the blur dramatically by doing that. There's more publications to be expected here. Back to the brick images. We then try to apply a different camera as well in order to compare what the effect of the optical blur would be in a different way. And we used the InGaAs camera to do that. And there's a couple of things which change with an InGaAs camera. Here I calculated the transfer function, PL intensity transfer function as a function of bulk lifetime again. We've seen this curve before. And now for the InGaAs camera, we see a much flatter transfer function. And that's mainly because I needed to use a short pass filter with a much longer wavelengths. That was because the signal, the InGaAs camera is much less sensitive, so I needed to increase the signal of the short pass image. But that means that we can't really measure low lifetimes very well because the gradient of the transfer function reduces dramatically. Nonetheless, we can measure high lifetimes well as well. Above 100 microseconds, we have a good gradient of the transfer function, and the result, the image result we can achieve, shows less blur, and that's because the quantum efficiency of the InGaAs camera is much higher, so we don't have any scattering in the detector. And additionally, we have a much better accuracy, absolute, because the quantum efficiency is very flat as well over the silicon spectrum. And so there's no uncertainty coming in from the not known decay of the silicon quantum efficiency. So we expect these measurements to be more accurate above 100 microseconds, and we can then use these to compare with the silicon measurements directly. And that's what I've done here. I compared the line scan of both. I could show you, there's a line scan taken of this white line, and we compared the accuracy of both measurements, silicon deconvoluted and InGaAs. And first of all, we scaled the silicon camera to the InGaAs in an absolute sense, and then we compared the relative change across the line scan, and we can see that there is a good overlap over a wide range. The InGaAs camera has a bit of sort of less blurred edges, whereas there is a bit of a not very good match on this side. So I looked into more detail there, and then we can see that the short pass image of the silicon camera, we can actually see polish structures, which affect the ratio, the intensity ratio, and that turns out in the bulk lifetime image, whereas that's not happening in the InGaAs image. This is mainly due to the depth of the signal. The silicon is filtered with 1,000 nanometers, so it means that we have a much more of a surface signal. It's a bit of a limitation of the technique in that way. Again, want to remind us what we've learned so far. So we have optical light spreading found to cause a major image blur in the silicon images. We measured the point spread of these, and we applied a deconvolution. The resulting correlation with the InGaAs camera's image is good, and the remaining issues are the electrical blur. And that's what I want to discuss next, is quantifying at least one physical limitation of this technique. So I look at the effect of the minority carrier diffusion and as well of free carrier absorption. To discuss that, first want to tell you about the PL signal, here normalized, changes with bulk lifetime depending on how we filter the image. If we filter with 1,000 nanometers, we have a very strong increase for short wavelengths, and then it flattens out. And then the longer we choose the wavelengths, the more uniform the gradient would be. If we then look at the images with the filtered with the same values, we can show a different contrast. We can see a different contrast of these images. Like for example, on the left, we see that we have a good contrast for the grain boundaries, whereas there's almost flat contrast throughout the grain. But if we then look at the very long one, we actually see there's still a bulk lifetime contrast. There's still a bulk lifetime change, which we just can't see here because of the transfer function not showing us. So if we then, sorry, I wanted to say something else. And so what I now wanted to discuss is that that there is actually a bulk lifetime change in these grains, and it is because we have lateral diffusion into grain boundaries. They come up sharper here, but there's actually we want to know the lateral extent of this diffusion and how it affects the image. And it represents the physical reality, but we want to know and be able to describe it in order to estimate more what would happen if we would cut that brick into wafers, and then at wafers we have surfaces and the carriers actually diffuse to these surfaces, not into the grain boundary. So it would be very nice to have an estimate in order to account for that. And so we set up a little model, and here we see like the bulk lifetime contrast towards the grain boundary, and we modeled that. We have a simple silicon grain with various bulk lifetimes, and a grain boundary with a very low lifetime, and we illuminate from the front, and then we calculate the excess carrier densities as a function of depth and as a function of lateral distance to that grain boundary for different bulk lifetimes. And we feed these profiles into the optical model of the PL intensity modeling, and then we can get a lateral function of the normalized bulk lifetime as a function of distance to the grain boundary, and then we can see how the depending on the actual grain lifetime, and we can see how the carrier diffusion affects the bulk lifetime in the grain depending on the distance to the grain boundary. And this could, in the next step, could allow us to apply an optical image processing and sort of sharpen the bulk lifetime images, which then represent more what's happening on the wafer basis. And I also quantified the impact of free carrier absorption. Like free carrier absorption happens, especially if we excite very deeply into the brick, and then once and the luminescence on the way out of the brick could be reabsorbed by free carriers, and that could affect the intensity ratio modeling. But I found that that if we can just find a change in the transfer function. Here's a function of doping for very high bulk lifetimes, which is relevant for monocrystalline bricks. It's calculated for p-type and n-type, and I also calculated what sort of the maximum impact we could expect. So here I show the relative impact at the Auger limit for p and n-type as a function of doping. And we can see that the maximum impact is always below 5%, but we know that we usually don't have very high, like background dopings up to 1e17, so we sort of happening more down here, so that we can actually say that there's usually not an impact of free carrier absorption on these measurements. Again, what we have learned so far, we've learned that filtering changes lifetime contrast, also relevant for wafer images. Lateral diffusion into grain boundaries changes local lifetime in the grain. We can model that two-dimensional. We can estimate the bulk lifetime as a function of distance to grain boundary and grain lifetime. And we can say that free carrier absorption mostly negligible. I want to give an outlook to the brick characterization. We can then use these bulk lifetime image to look into impurity analysis. We can analyze full spectrum, which we have done already. So we can then apply the full spectrum modeling and show that the modeling we've used for these images actually fits with the reality. So we have measured spectra, which we can fit to the model very well, and we can do other things with these, like full spectrum bulk lifetime analysis, etc. And we hope we can use these images for efficiency predictions. And we will look into, we plan to look into inline measurements as well, which means measuring on the fly in line scan. Now presentation swaps to the inline inspection and sorting Westcott wafers. This data is supplied by VT Imaging, and yeah, as you know, as you could also see on the brick, that Escott wafers very vastly in quality, which means they vary vastly in impurity concentration and dislocation concentration. The impurity concentration shows up with the effective lifetime contrast, which we see in PL images. It's high impurity concentration in this corner waver. And the dislocation show up as well. And BT imaging now made it possible to inspect and classify these different types of wafers at inline speed. And that, for example, allows here to classify dislocation defects. So we have a S-cut PL image, and then we apply image processing, and we can classify dislocations and come up with a matrix which is non-disclosed, but basically we can come up with a defect density, and that's correlated with the various cell parameters very well. And this is just one study. This has been done by several institutes around the world, and it has been shown that basically the the IV data strongly correlates with any sort of proprietary type of defect metric. So there's been studies from Fraunhofer, there's been studies from NREL, and what's sort of interesting about these is that there's actually no lifetime information used for these studies. It's a really purely image processing technique. And there's a new publication about this, that we can also use the defect band to image. And so up here we have a PL image, but down here we have an image of the same waver measured at the defect band. The defect band is around 1550 nanometers. So if we filter, this image is filtered with a short pass at 1300 nanometers, and this image is filtered with a long pass at 1300 nanometers. And we get pretty much the inverse contrast. Here, like, the dislocations show up. Here the dislocations have a low count rate. And they were able to, again, correlate the defect area fraction with cell parameters and efficiency. And with the impurities, it's possible to find signatures for certain types of impurities, for ingot edge, transition areas, corner areas, and fully impure areas. And then BT imaging studied sort of the production line of several companies, and they rated these impurity signatures and the dislocations in a non-disclosed way, so that we have a dislocation bin and an impurity bin. And what they found is that for this manufacturer, this is data of a manufacturer, they found that the efficiency is the dependence of the efficiency on the dislocations is weaker than usual, whereas the dependence on the impurity fraction is higher, and which then can say that there is that the manufacturing line shows a poor gettering efficiency. If you would compare that to other data, which I'm not showing here, you can see that very clearly. So what it means, you can use image processing techniques to, for example, show that the production line shows a poor gettering efficiency. And then now go towards an example for how you can characterize advanced cell concept with submicron resolution. And Fraunhofer has been published a technique, it's called micro-PL spectroscopy, by Gundel et al. And they were able to image very small structures. So this is a PL image, and they were then choosing just the grain boundary here, image that with micro-PL, and are able to investigate grain boundaries very well. This is just one example. Another example is that they were able to investigate nickel-plated front contacts in their doping concentration. So this is a nickel contact, and they were actually able to, well, they polished, they sliced the sample and polished the sides, and then looked at the side profile, and they were able to look at the doping concentration. And for this sample, they tempered at 500 degrees for 10 minutes in order to emphasize the sort of the effect of low lifetime under the contact. And they were also able to do that at laser doped back surface fields, and showing the boron concentration and phosphorus concentration after a laser doping. And published by Gundel as well. Yeah, and I want to conclude and give an outlook. So you can see that PL imaging shows an increasing number of quantitative applications. And one quantitative application is brick imaging, and it could become a valuable technique for early stage characterization and as a prediction tool. And qualitative images contain much more than just effective lifetime imaging. They can use for S-cut sorting, gettering efficiency, and efficiency prediction. And microscopic PL is a candidate for research application for local doping structures, local recombination activity, and defects. And in conclusion, PL keeps playing a strong role as an ideal characterization tool for solar cells and devices, solar cell materials and devices. Thank you.